We will talk about thermal energy and competing uses in underground space. By we, I mean, of course, not me, but the two speakers we have today. So there is Burkhard Sanner, who is an expert in geothermal energy, and he will give an overview on this technology. I'm very happy that he agreed to join. And afterwards, we have Sebastian Bauer, who is professor at the University of Kiel, and he's working, among other fields, in the field of competing uses in underground space. So I'm very pleased that the two experts are willing to share the information today. And yeah, with this, I will give the stage to Mr. Sanner. I will stop my screen and then you can share if it's working fine for you.
Good afternoon. We'll in a moment try to show my screen, yeah. But I will not show my face anymore because my internet connection is rather weak here, so it's better to not try to overload it. So let's jump. Yep. And let's put that in full screen. No. Okay, do you see my screen?
Yes, perfect.
Okay, fine. A few words to myself. I'm actually retired meanwhile, so but it's a pleasure for the IEA energy storage program to give some of my thoughts and experiences in past almost 40 years in this field. I used to work with the University of Gießen while I was involved in IEA projects since several years. I did some consulting work with UBEC, a company that you see here the coordinates, and that I use the template for. I'm still involved in projects with UBEC, and some of what I'm showing you was also done under their leadership. Okay, let's go directly into the underground. The opportunities that the underground offers for, let's say, a constant thermal environment was known since a long time, and people have used it. So for living underground, for instance, like in these two examples from Turkey and New Mexico, but also for storing some goods. I have here an example from the UK, but we have this kind of ice houses or ice cellars throughout Europe in many places. The Romans, the Egyptians already used this technology because we have a constant temperature in the underground, and we have usually quite good insulation around the underground storage area. But we have some boundary conditions to think about. The one is that we have a temperature which is varying close to the surface. There is an influence from the climatic conditions, the weather conditions on above the surface, and then this decreases towards depth, and in about 10 to 15 meters we don't see much anymore. So this is an example from measurements I did in '88 in a research station which was part of an IEA heat pump project, not a storage project. Different implementing agreement, but anyway, you see that about 9 degrees is the temperature in the so-called neutral zone. Beneath these depth, we have an increase in temperature towards depth, and this is controlled by the geothermal heat flux. The heat processes in the underground are rather slow. So we have from the one, these, let's say, background temperatures controlled in the upper part by the climate, in the lower part by the geothermal heat flux. Of course, the thermal conductivity of the underground, both in terms of convective and of conductive heat transport, is important. And in consequence, we have usually in the depth that we address here, a relatively modest temperatures and a very slow heat transport process. This makes UTES typically suitable for a seasonal storage. So UTES is seldom, only in, for instance, the case of caverns, used for a short-term or daily diurnal storage. Usually it is for seasonal applications. There are some basic concepts. We have the aquifer storage, where groundwater wells are used to access the underground. Wells where groundwater can be extracted and also be infiltrated into the underground. We have the borehole storage systems, where borehole heat exchangers are used, closed loops into the underground. We have cavern storage, where either natural caverns or artificially made caverns are used for storing, for instance, water with a certain temperature. These are the basic concepts that are in use. There are some that are not really underground. We have pit storage systems that are partly underground. We have some water tanks buried in the underground. There are some examples in Germany, for instance, of large water tanks buried, but this is not what I'd call underground thermal energy storage, because there an artificial vessel in the underground is used and not the underground itself. So these are the concepts of UTES. Looking at the basic opportunities that these offer, we can distinguish the energy sources. That's where we get either cold or heat from, because we can store both cold and heat, or both simultaneously. Let's say not simultaneously, but in the same ground or the same installation, but at different times. So we have the source, we have the medium where we store the energy, and then we have the use of the energy. So we have cold storage. That's when we use either ambient air in wintertime, which is cold, surface water, the cold from the heat pump evaporator or chiller. We can store heat, either from solar heat, from collectors, from street surfaces, which is done, for instance, for snow melting installations, geothermal heat, waste heat, industrial. Meanwhile, I prefer to call it industrial residual heat, because it's not wasted anymore. The storage medium, as said, can be the groundwater, if we are talking about ATIS, groundwater in a groundwater-bearing layer, an aquifer. It's soil and rock, when we use it with the borehole heat exchangers or with energy piles, or it is water, usually when we use caverns. And then the use, it could be for refrigeration, direct cooling, space cooling, or process cooling in industry. We have some nice examples on that meanwhile. Or we have heat storage for space heating, domestic hot water, process heat, and street surface when we're talking, or any surfaces when we are talking about snow melting. So there are a variety of different technologies or different combinations of what you see here used in practice. There are some basic constraints we have to talk about. This is just to say a very basic concept of the energy source, the storage, and the energy use. And I'd like to talk about the loading and unloading temperatures in a moment. So that's where they are. The temperature into the storage and temperature out of the storage. This is what we're looking at now in the next slide. One specific character or property of UTES is that we seldom get the same temperature back that we inject. So there is a temperature gap between the loading temperature and the unloading, when we start unloading. In ATES or CTES, when we are using water, in particular in CTES, which is more like a tank, this temperature gap in the beginning can be very small. But when we are talking about BTES, where the temperature is used in thermal conduction to extract the heat again from the rock, that can be 5, 10, 20 Kelvin, a temperature gap that we need to get the heat back out of the ground. So that's one point. When considering that it's both the case for heat or for cold storage, this is only showing here heat storage, but it's the opposite in cold storage. The other point is that the temperature usually decreases over the time of unloading. So we are not looking at, for instance, phase change materials or something like that, where the temperature remains fairly stable for some time. That we have a sensible storage, and temperature usually goes down over a certain period until we reach the minimum unloading temperature, which is usually the return temperature of the system, which cannot be anything below that temperature cannot be used from the store. By the way, there have been in the last years some attempts to use phase change materials in borehole heat exchangers, in fillings for borehole heat exchangers, for instance, to somehow remediate that, but the amount that would be required for actually seeing some effect is much too high to be practically used in any way. So these basic constraints, we will never get back the energy at the maximum loading temperature. The unloading of the store is limited to the lowest temperature the energy use system can handle, which is in practice the return temperature from the energy use. And our storage efficiency is controlled by thermal losses. That's one item, of course, thermal losses of the store. And the usual usable temperature difference between the initial and the final unloading temperature. A few words on history of UTES. We have, as I showed in the very first slide, some basic concepts of using the underground, I think, since mankind is on Earth. That practically in more technical terms, it's used since about the 1960s. There were large installations for recooling of groundwater that were used for cooling purposes in textile industry in China. And because the groundwater was heating up, that was recooled again, which is basically a cold storage application. Early ATES cold storage, but of quite some size. Like we see often in China, that also with modern BTES systems or ATES systems that tend to be really large. I've seen in China BTES systems with well above 1,000 borehole heat exchangers. So that's not uncommon there. For the heat storage in the ground, the use of bore heat exchangers was first, to my knowledge, first proposed in 1964, when solar energy storage in the underground was considered. And then we had some suggestions for use of aquifers to up to quite high temperatures, 170 degrees C. In both cases, there was some link to nuclear power plants to make use of waste heat from those for use of aquifers. So that was in the 1960s, 1970s, the idea came into the publications, but the practical application, that was a little bit later. These are some of the milestone installations. I'm not going through those, just to give you, if you look at the year, it's mainly in the early 1980s, and that is exactly the time when the first IEA energy storage projects were running. I have here some generic system configurations. I reckon that due to time constraints, I'd better not dwell too long on those. You'll have a chance later to look at the slides and see the concept behind that. So we can have cold storage without a heat pump. This is a simple cold storage system where in wintertime, cold is stored in the underground and used in summer for cooling. One early example for that was Perscombinatie in Amsterdam, a printing company that used an aquifer for cooling of their printing shop. The solar collectors can be used. This is plain heat storage, while the previous one was plain cold storage. This one is plain heat storage. I'll show one example later on. Very frequently we see that we have cold and low temperature storage with heat pumps. Low temperature means in the range up to 20, 25, 30 degree. This is the classical large ground source heat pump layout that we see here. So large ground source heat pumps usually have a part in the operation which is actually storage. So the distinction between UTES and large ground source heat pumps is very difficult to do. And we had once a definition in one of the early annexes, Annex 7, Annex 8, to say that if 25% of the annual turnover is outside the store or outside the bore heat exchanger field, we call it a ground source heat pump. If it's less than that, then we call it storage. And finally, heat storage from industrial waste heat. That's something similar to the solar heat, but because we have industrial processes generating heat all year, it's summer and winter, and in summer there is little use of the heat, so it can be stored in summer for use in winter, and in winter it can be used directly. This is a bit specific thing, but I put it in here because I saw that there is a new annex or a new task, as it's called now, 38, looking into snow melting, and that's exactly what this concept is for. A few examples. This is one with the solar heat, pure heat storage. There is no heat pump involved, at least not at that stage that's shown here. The peak heat is done with natural gas boilers. It's a famous example. Most of you might have heard or seen of that in Neckarsulm in Germany, with 528 bore heat exchanger to a depth of some 30 meters, because geology didn't allow to go deeper, there was a layer with groundwater flow beneath that. So the heat is stored in summer and is used in winter for heating. And in summer, it's of course also domestic hot water is done with the solar collectors directly. You see it under construction in 2001, and I came back later on and looked at the place, and you still can see the traces of the beaters. Beneath these kind of sun decks that you see here are the shafts for the connections of the manifolds of the bore heat exchangers. In the background, you see one of the accumulators of that's water tanks that are used as short-term storage. It was a successful example, and I heard that they plan to do something similar in the community now. Another one, this is an example for the, let's say, classical ground truss heat pump system, acting partly as beaters. The headquarters of the camera manufacturer Leica, new headquarters built in 2012-2013. And the bore heat exchanger field is beneath a parking lot in the left side of the picture. And here it is important to look at the extension of the thermal influence. So the maximum extension in summer and in winter is shown here on the left side, simulated to get an idea of what the operation would be. And this plant is now monitored to show if it really, let's say, fulfills the prediction that were done. An ATIS example now, also a famous one, the buildings of the German Parliament, the Reichstag, which is the building in the photograph in the lower right background, and other buildings for the parliamentarians in the left background. Those buildings are in a kind of, let's say, district heating system, small one. They have a common heat supply and cold supply. And there are two storages on top of each other. Are cold storage ATIS, mainly for cooling of the parliamentary or parliament building itself, operating at temperatures in the range of 10-8 degree, and beneath a sealing layer, an aquitard, a water impermeable layer, is the warm ATIS with temperatures up to about 70 degrees. And everything is connected, and the two set of wells for the deep aquifer are directly in front of the Reichstag building, and the other set is north of the parliament, the office buildings of the parliament. Again here, and it's really important to look at the extension of the, let's say, thermal influence. This is from Geothermal Brandenburg, GTN, a simulation showing the extension in October 2008, after full summer heat injection at the lower of the two well groups. We have quite a number of greenhouses with ATIS in the Netherlands. IF Technology is the champion of that since many years, and very active in IEA since a long time. I'm not sure if there still are, but they used to be. There are many more now. This is a picture from about 10 years ago. And that's my second last example. It's a little bit different in concept because we're talking about deep ATES. This is about 1 kilometer deep boreholes, a former geothermal heating plant that was converted into a ATES using heat from a cogeneration, heat and power cogeneration plant that's shown in the lower right, to store the excess heat in summertime from that plant for use in wintertime in a sub-network of the city district heating network. Again, here, a thorough investigation was done, also monitoring. Here, the simulated extent of the thermally influenced zones after the recharge session in 2007, so that you can see there are two wells, one in the warm well in this case, another the cold well, so it's heat storage only. And well, it's more than 57 degrees C. It's just here the let's say the boundary, but the injection temperature is in the order of 80 to 90 degrees. And the final example, ground water heat pumps for the Bonner Bogen project, built around 2010, and meanwhile extended and enlarged. It's on a it's a reclaimed industrial site in Bonn, built into offices and a high-class hotel with wells. You see here the location of the 6 wells let's say in relation to the buildings. Shallow wells, because it's just looking at the terrace, the gravels of the terraces in the underground in the Rhine Valley. And it's for about 1 megawatt of heating and cooling. Here it was important, again, to look into both the hydrogeological parameters, so that's why well pumping tests were done here, and also simulations to make sure that the 3 different plants that are in near vicinity to each other do not interfere with each other. Okay, I have a few more slides on the history of IEA ECES. I'm not going through those, but you may have a chance to look at it. So this is just here the last one. I saw that you have now a new task, large thermal energy storage for district heating, something that we talked a lot about in the past also. And I'm happy to see that these things go further, and that Wim van Helden is a task leader. So I think that will be a good result that he's bringing. Okay, some idea of drilling for the large borehole field at Leica, 80 boreholes. So they had at peak times 4 drilling rigs simultaneously working to achieve that into in a let's say a reasonable time. Okay, almost half an hour anyway. I thank you for your attention, and happy to answer questions.
Oh, many thanks, Mr. Sanner. This was a very good overview. It's not my background, and now I really have a good idea what is possible, and also what diversity exists in how to use it. Very interesting. I'm not sure if there are already questions. If someone raised the digital hand, I would probably see. If not, I can read the one from the chat. There was one from Mark Howitt. So there are a couple of questions. I will just read them. Maybe
I can see them myself.
Yes, the thing is, I have to read because we also make it available online, and you cannot read what is written in the chat.
Yeah, okay.
Yeah, that's a bit the problem of this digital world. So just So the UTES has a rate of heat loss. What is the rule of thumb, OC per week? And following, what are typical recovery rates, i.e. what percentage of injected heat can be recovered, assuming zero time-based losses? For example, temperatures below a threshold are not usable. Not all the injected hot fluid can be extracted again.
Yeah, that's right. I cannot give you anything in Kelvin per week or something like that of losses, because that's very, very different in the different installations. We usually have not very well controlled environments. So we don't have an insulated tank where we know exactly the geometry and the insulation thickness and all these things. We have no phase change material where we know exactly the properties and so on. So what we can say is that in an aquifer storage, usually the losses are less if there is not a high groundwater flow in the underground, of course. We can extract more because the injection and extraction is done by pumping. So we change the pressure in the water table there. And we do not need to change the temperature to move some heat around. That's a difference for the beta systems. In the betas, in the conductive situation, we need to lower the temperature to get heat out of the ground, or to raise the temperature to get heat into the ground. So there, the losses are, at least in the unloading and loading operation, much higher. The losses, if you leave the store alone, are not too high. So there was an example from a high temperature plant, an unsuccessful one because they couldn't get the heat out again in France, in near Paris, in the 80s. But what they could do is to read the temperatures from the sensors still, sensor in the ground, and after 3 years, they still had an elevated temperature that would be in the order of about 60–70% of what was ejected still was in place. So the, let's say, the losses as such are not too big, because we are talking about large volumes, meaning the surface where losses can occur is smaller compared to the volume that we store. The storage efficiency, so the recovery rate, so to say, that changes somewhere between 50 to 70%, depending on the size of the installation and the allowable temperatures and such. The nice thing with the ground source heat pump systems is that we use it both for heating and cooling, so there are virtually no losses in this case, because with a heat pump we can actually go beneath this unloading temperature. I hope that was clear enough.
Yes, in my opinion, yes. If not, please just write in the chat, and then maybe we can forward directly. Many thanks. So if I may ask a question as well, as there's in the moment no other question. Now you have I guess you have seen a lot of things that were developed the last decades, and I wonder, is there, in your opinion, something which should have gotten more attention, or like it has been a little bit overseen, or yeah, something like this?
Well, the one is or was the snow melting. That was an interesting application that we talked about many years ago already, and which was for some time sleeping. And I see that you have a new NX38 that's looking at that. So that's interesting for me. The other ultimately high temperature underground storage. I myself, I was operating agent of the NX12 for the high temperature underground storage, which means something about between 50 and 80 degrees C, so it's not really high temperature. That is very helpful for applications, for instance, district heating, and I hope that your new annex on that will look into it also. We've seen very little development of that, but it's interesting to use in these cases this industrial heat, residual heat from industry. Mm-hmm. We have there is a foundry in Emmaboda in Skåne in Sweden that stores heat from this foundry. They are making pumps, and the pump cases are done on site, and store it in a vitas and use it for heating of buildings in the winter time. So that's temperatures we are talking about close to 100 degrees, that the foundry has very high temperatures. And we have several of these installations, meanwhile, in industry, where industrial processes are cooled and the heat is used for heating. There is an ample opportunity, but it's usually very tricky in details, and also in industry, the payback times that are allowable are much shorter than when we're talking about residential installations. I see there is another one in the chat.
Yes, there's, I would say one more question, and then we can follow maybe with the next talk, just to stay in time. And if you want to, Mr. Sanner, you can maybe answer in the chat directly, just to don't leave the people behind, or maybe at the end, but I don't want to skip the time too far to the end.
Okay. We should give my fellow speakers some chance to.
Exactly.
Thank you.
So even tomorrow is for most of us a holiday. I don't want to stretch it out unnecessary. But I would say I would give Gerhard Sotter the question a chance, and then maybe Mark Hobbit, you can write directly. Yeah, sorry if it's.
No, I see what he's written, and I'll try to. Yep. Okay.
Okay, so okay, I will just make this question as I announced now. From Gerhard Sotter was, if we store it at high deep, we could even gain heat input instead, have heat losses, or is it in focus to go below 1,000 meters?
Well, then we are in the real geothermal plant. This is we will not really get gains, because we are talking about temperatures of 30, 40 degrees at the depth, 40, 50 maybe in places. So for heating purposes, it's not enough. We would have to go further down to really have heat gains in our storage. But the idea is, if we are too close to the surface, also the influence on groundwater and on the surface itself, so maybe too high. So there are environmental constraints that we need to consider. If we are at 1,000 or more, that's not a big problem. But on the other hand, it's much more expensive to go to that. And usually we are talking of water that has mineralization. So the water quality and possible corrosion, scaling effects, and so get problematic. And that's why, beside the one plant in Brandenburg, which was a geothermal heating plant before, I've not seen any further HS at this great depth.
Okay, many thanks. So then let's go on with the second speaker. Mr. Sebastian Bauer, sorry if it's a little bit of a delay. It's always a mixture of finding time for discussion and also having the talks.
Okay, so I hope that worked and you can see my screen now.
Perfect, yes.
Yeah, okay. So thank you very much for having me here. I will talk about, I have a pretty lengthy title up here, and there was a long title for today's talks, and I'm concentrating on the second part, which is basically the subsurface space required. So I'll talk about storage potential, storage integration into energy systems, quantification of induced impacts, and the subsurface space required. And I will talk on all of that on the example of gas storage. So we will have a change of, say, storage application. Yeah, but the concepts, I think, are pretty much the same. Yeah. So if I move to, say, 30 years in advance, the year 45, yeah, then we are faced with an energy system which, at least for geoscientists like me, looks somehow like this. So we will have sectors like power, heat, and gas, and while we will have a national power and gas grid, yeah, because we already have that and we are strengthening that, we will have heat networks basically on the local level. Yeah. And so this is one of the differences, and we will have supply side like wind power, hydropower, solar power, for example, for electricity, but we will need converters between power sectors and the other sectors, like a combined heat and power plant, yeah, or a heat pump, which is also there, or electrolyzer, or a turbine, and they go between the heat and the power sector, or between the gas and the power sector. And we can also basically go from the gas back to the heat sector by, for example, using a gas burner like we do now. Yeah, and if we look at all these sources we will have, and the time frame and their fluctuations, yeah, then it seems pretty obviously that we will run into storage demand, which will both be on the national level, but also on the regional and down to the local level, and maybe even on the very small scale level as well, just to deliver the energy security and the working of this energy system in total. If we now move to the subsurface, yeah, we've seen thermal storages right now, so I have them here as well, but this is basically all the storage options we've looked at the university here. And this is like power to gas or power to liquid. Yeah, so we can make gas or liquids. We can convert it to compressed air energy storage. That's a mechanical storage, yeah, instead of a chemical storage. Yeah, or we can convert power to heat, or we can directly collect heat and store the heat. Yeah, so that's power to heat and heat to heat. So this is all the storage mechanisms and ways of getting to something we can store. Yeah, and down there I try to sketch basically the scales, both in storage amount and in cycle times, which are available. Yeah, and we can see that especially for the gas storages, we can reach very high storage capacities, in the up to the terawatt-hour capacity. And we can also reach seasonal cycle times. Yeah, but we can actually also go down a lot. Yeah, and so as an extension maybe to the speaker before, we found applications, if we look at heat storages, where we can actually operate them on the daily scale and reach megawatt hours of a megawatt of power with ATES or BETES systems. Yeah, this requires quite some installations, that's true. Yeah, but these systems can also cope with short cycle times. At least that's what we find. If you move to the subsurface and do storage there, especially large storage, you may not be the first to go there. Yeah, other people may have other ideas of what to do in the subsurface. And this is also one of the problems. If you build, for example, heat storages, yeah, there may be groundwater uses there. So people want to use the groundwater for drinking purposes or for industrial purposes. Yeah, and so there's other types of use which you have to account for. And so you have to organize the types of uses, and you have to find out, are there impacts from one use to others, and how do they look like, and actually are they positive or negative, or can we neglect them? Yeah, and a few ideas are basically up on the top left. Yeah, so there's the storages, the gas storages we have, but there's also the heat storages. Yeah, and you can see in red, But then there's also like groundwater production, there's mining, there's deep geothermal systems. Maybe there's even still some hydrocarbon production around, which all basically is something going on in the subsurface. And if we move to heat storages and, for example, urban environments here, then you may have not only groundwater uses, but you may have tunneling, you have infrastructure which is there and in place. So you have to look at the impacts of those as well. So if we want to look at this, then we need to know the subsurface as a storage medium pretty well. We need to know how are we going to use the storage. So we need to define temperatures, we need to define the capacities we want, we need to define input and output rates, so that we can basically characterize, I call it the intensity of the use. And from that, we can then sort of determine how large such a storage site will be, after we know how it's going to be used. And then we can also look at induced impacts. So do we have temperatures which travel because we have heat losses? Do we have hydraulic impacts because we move water around? Do we have mechanical uplift or settling? Do we have geochemical reactions which do something with the groundwater? All of this then we can look at, and we can from that then deduce the subsurface space requirements. So this is basically the logic if you look at this subsurface space requirements. And so there's a small advertisement slide here, which is for basically the Angus project, which was looking at the impacts of the use of the geological subsurfaces in energy storage. There were some research institutions involved in doing that, but I want to mainly use this here to thank the people who sponsored it, which was the Ministry of Bildung und Forschung and the Ministry for Wirtschaft and Energie in Germany. Which basically sponsored this project as part of the Energiespeicher. That was a research initiative. And within this project, we developed concepts and methods for planning the subsurface. We did numerical scenario analysis to test these methods and develop them. But as a basis, in green and blue on the slide, you can see we did some parameterization, we did model development. And in the following slides, I want to show you how we fill this approach, this general approach, basically for gas storages, to illustrate all of that. So what you can see here is basically pictures of North Germany, sort of funny. I hope you can see my mouse. So this is part of North Germany, and this is the German part of the North Sea. So up here you would be in Denmark, and here you would be in the Netherlands, and if you go over here, you enter Great Britain. So what's depicted is the presence of storage formations where we can do gas storage. And there's mainly 3 storage formations. One is basically pretty everywhere. This one is just in places, and this is sort of mainly onshore, at least in this part of Germany. So we know where the storage formations are after we've made the corresponding models. Then we need to also know the parameters. So here's just one example of one of the parameters we need, which is the porosity, because we put the gas in the pore space. And on the right, this is basically the approach we developed to evaluate all of that. And here just one highlight of all the results. If you want more, there's a pretty new paper here from a PhD student of mine, and this shows capacity and rates for hydrogen storage in a porous medium, which we can achieve. And each of these balls is one storage opportunity. It has one storage location somewhere, and there's a range of depths we can go to, but which you can see on this axis, but you can also see there's a range of sizes we can go to. And if you look at the numbers, then we really go to hundreds of terawatt hours in theoretical capacity. We all know, we also looked at the rates. We had the topic before that the geothermal storages may be rate limited. They're not very fast always. And the same is true for this as well, but you can see we can reach basically power rates in the gigawatt range on these storage sites. So we estimated huge storage capacities which are available. They're pretty evenly distributed. all over the place, and we found a total of 74 sites. And basically, the potential storage is much larger than what we think will be demanded in future. So the good thing is, then if you have more than one, then you can put additional constraints on it. Yeah. So where do you want it, and where do you locate it? You can sort of look for optimal places. Yeah. And for that, we developed something called an energy atlas, yeah, which basically puts together all kind of information you would want in order to decide where to build such a storage site and what to use it for. And so this combines geological information, it combines information from the power sector, from the heat sector, from energy production and transmission. So it has power lines, it has pipelines, everything like that. Yeah, and it has restrictions from spatial planning on the land surface. Yeah, so if there's restricted areas where you're not allowed to build or put a pipeline or anything like this. Yeah, and I'm sorry that this is basically a German slide, yeah, but this is from this energy atlas. And this is just one example where we can see power plants, solar power plants, biogas plants, power lines, and the subsurface storage formations as one basis for planning. If we want now to decide how we use such a storage site, then we need to know, okay, what's the purpose of the storage? What should it do? Yeah, and in order to tackle that, we build a coupled. We need a coupled model, yeah, and we also built one between the energy system down to the geostorage, yeah, because the geostorage has a direct. It's just one part of the overall energy system, so we need to define its role there and its purpose. And for doing that, we made a three-step approach. So we had a model of the energy system, we had a model of the power plant, pretty detailed, which is here in the middle, and we had a pretty detailed model of the geostorage. And we needed to couple these models and run them in combination in order to find economic uses of such a storage. Yeah, so when there's wind power, for example, which I can convert into hydrogen and which I then can store, yeah, and when would I need it back, and how do I have to design the energy system in a way that there will be enough wind parks to generate enough hydrogen so that we can fulfill the demand later on. So this is what you can only look at if you have such a basically holistic model, which goes right down to the thing and couples everything. This is a quick look at the three kinds of models we used and developed. Yeah, so there's a model for the energy system, but there's a number of models one could choose from. There's a pretty detailed model for the power plant, yeah, which models the details actually and all the flows in the power plants. Yeah, and then there's a geostorage model, which does the same for the subsurface installations. And if you run all of these models jointly, yeah, so we developed pathways, scenarios for the future. So on the top left, you see a number of lines, yeah, and they represent different projections of the energy system into the future. So this is the national energy system for Germany in the year 2030 as the black line, in the year 2040 as the red line, and then 2050, there's two options depending on how much biomass you're going to use. Yeah. So there's some decisions to be taken, yeah, but you can, the good thing is you can now feed them to the model and ask the model what will be the overall outcome. Yeah, and we can see that the storage demand, yeah, is highest for the red line. Yeah, this is basically the largest change. So this corresponds to the largest storage demand. Yeah, we will actually see intermediately, yeah, somewhere on the way, at least in these scenarios. On the right, you see how this looks in the subsurface. So there's a number of wells we are going to use, yeah, and there's one geological storage trap we are using for that. What we found is that basically all of these futures our colleagues from the energy system develop, yeah, we find uses for storages, large-scale geological storages. And once you have one, yeah, they can be adapted to the different scenarios. They can be made larger, they can also be made a little bit smaller, yeah, and they can change their power without changing the capacity too much. Yeah, so there's quite some flexibility in that if you go into the detail. Yeah, and we found tens of terawatt hours capacity, yeah, for example, hydrogen or synthetic methane storage. Now the question is, how big is that? Yeah, how much space does it take up? So we divided that in our concept into the idea of something like an operational space. This is the space directly used for putting energy in and taking it back out again. Yeah, and this is on the order of 3 to 3.5 kilometers on the diagonal there, as you can see on the left-hand side. Yeah, but we also move water around and we move gas around in such a big storage site. Yeah, so the pressure actually travels much farther. Yeah, and pressure responses larger than 1 bar are basically on the order of 15 to say 17 kilometers for this instance, but they're decreasing with the distance. Yeah, so it's becoming smaller the further away you go. Yeah, and once you move out of this distance, yeah, you basically see nothing of the storage site. So you wouldn't notice whether it's there or not and whether it's there. What we can see on the lower figure actually is it depends a lot on how you actually operate it. Yeah, so even for telling you this affected space and the size of it, we need to know how the storage will be operated. Yeah, what kind of rates, what kind of loads, whether it's mainly seasonal or monthly loaded and unloaded. Yeah, this will determine basically the impact on the subsurface. And once we have that, we can actually also look, okay, would there be a neighbor? Yeah, and would the neighbor be impacted? And we looked at that. So we put it's all synthetic because it doesn't exist in the north of Germany. So we put a synthetic hydrogen storage next to a synthetic methane storage. Compressed air energy storage, yeah, because that even has a larger pressure impact. Yeah, and we worked them individually and we worked them at the same time and saw how do they impair each other. And at the lower part, you can see the pressure response, both at the hydrogen and at the compressed air energy plant, with and without the other plant actually working. We can see the changes are actually very small. Yeah? And sometimes actually the change is supporting the operation of the other plant, yeah, because we have like pressure losses. And if you push a little bit from the side, this actually increases the probability that you get the gas back. Okay, so I tried to show you the approach, the general approach, and how that looks like. So I think we have suitable storage technologies and very large potentials, both onshore, both offshore, both for the gas, both for the heat. And at least for Schleswig-Holstein and for the gas storages, we've now made a pretty systematic estimation of the capacities and the rates available. Yeah. If you want to actually look what's the sense of such a storage site and how should it be operated, you need to go from the energy system to the individual power plant, yeah, heat pump, whatever it is, and then to the storage and combine this. Yeah. We think, after looking at all this, that geological storage can significantly contribute to a stable and reliable future energy supply. And we found uses for all these kind of storages in basically all the futures we could define if we go to 100% renewable. Yeah. So if we go to real high renewable parts of the power system. Yeah, we are right now in developing the planning instruments you would need. Yeah, so you can see we can actually size, dimension such storage sites and tell you how big they are. So we could decide whether it's a nuisance or whether it's okay and whether there's neighbors who would feel impaired. But you would need these realistic load cycles for that. And there's an afterthought, which is right at the very bottom of the slide here. I think this geological subsurface is an essential social resource, yeah, which we have to manage all together as a society and not just give to individual companies to manage their part. Yeah, so such an overall planning approach, I think, is necessary actually for public acceptance and for getting the long-term stability into the system as well. Yeah, so the start for a framework, I think we could build or is there. So thank you very much for your attention. If you want more information, you can go to this internet link down there or just contact me or ask me now. Thank you.
Many thanks, Mr. Bauer. This was a very nice overview on the work you did. And I can imagine it's quite a lot of effort to have all these models working together. And yes, looks incredible, the outcome. And very positive. Well, I couldn't agree more with the last point you just mentioned. Very interesting. Don't know if you have already a question, so there's no hand raise. Also not in the chat. And meanwhile, I would like to ask, just as it just fits to the topic before, you just showed an example where you have a compressed air storage and also a hydrogen storage. So did you also consider what happens if you have, like we saw before, borehole storage or anything of the examples we had before of the interference between the systems?
So we are basically at the stage where we've developed the tools we need to look at this. Yeah. And it's a bit easier to apply this on the deep geological subsurface because the individual storages are much larger, and they're pretty much alone on there. There are some hydrocarbon uses in the north of Germany, but they will probably phase out, at least definitely until 2050. So we have to look at geothermal, and we have to look at storages and all this kind of stuff. But this is large scale and not, so it does require a lot of information, but at least for the north of Germany, it's there due to the hydrocarbon history we have here. Mm-hmm. If we move to heat storages, it's actually the same. So we have the tools in the project, but it's difficult to get the amount of information you need because heat storages are much smaller, they're much more local, and you would build them where you need them, which is inside the city, or actually in that case, underneath the city. And then it becomes very complicated to get all the information you need on basically the small scale geology, and how that's not always available, as we found. Or to put it realistically, just very few towns and cities in Germany actually know their subsurface. For most, it's pretty unknown, and there's no generalized models or whatsoever. You would need to include information on, say, subways, pipelines, deep growing fundaments. There's like parking houses which go 2-3 stories in the subsurface. You would need to include all of this in all detail into these models, because this already impacts such storage sites as we saw. I think Sanner showed pretty clearly, if you go to one of the storage options, which is the BTIS, it directly starts at the Earth's surface. So this is where you start. With ARTIS, you're freer because you can basically put it to depth and vary the depth. If you have 1, 2, 3 aquifers, as you sometimes have, then you can maybe choose one. But also you're not free because I'm doing one project right now here in Kiel, and we see one is used for groundwater purposes. So we cannot go there with such a heat source. So in principle it's possible, but it's just a lot of work. And because you're really close to the people, and that again will, I think, stress the last point. Because you're so close to the people and right in the middle of the city, you will need the acceptance for that.
Yes, I see. So this is a different point to think about. Many thanks. So there was one. Okay, now there are 2 questions. One from Mr. Sanner. Geothermal energy in Germany is subject to the mini-law BERG. What about compressed air and how to regulate?
So it's the mining law, and the same is true, So you're using public subsurface space if you would go for compressed air energy storage or for hydrogen or whatever storage. So you would need to apply under the law of the Bundesberggesetz for a permission to do that with all those steps which are there and required. But that's basically defined how to do that. And especially for the large ones, actually, we have a few of those, and I think some of those were just very recently in the newspapers. And we also found out that it's not a good idea to sell your own gas storages to your supplier of gas, if both is the Russian state. Yeah.
Yeah.
Okay, so I just read the next question. Yeah.
Yes.
Are you planning to incorporate CO2 storage in the model predictions? In principle, we could include that because it's just another type of a gas storage, except that you don't want the gas back right now. I'm not so sure in the future because we are going to run into a carbon-free energy system, basically, if we are all to wind and solar power. Yeah, where do we get the carbon from for all our chemical industry? So it might be that we store CO2 now, but we want it actually back later to make synthetic fuels. So that could be the use of actually getting that. Yeah, we could include it. Yeah, but right now there's nothing planned in Germany, so I wouldn't know what to include. Yeah, and I would need, okay, how many million tons would you want to store, and roughly where, and then it could be incorporated in such a planning process. And we, of course, could incorporate like 10 such sites into the model. So the concept and the models and the system would work for that.
Okay. Many thanks. So I think we have to close here. We have a little bit over the time. Anyway, many thanks for you two presenters. It was very interesting, very nice. For me, new views into this topic. And I guess a lot of work already came into this. So thanks again, Mr. Bauer, for your talk and the answering of all the questions. To you as well, Mr. Sanner. The next time it will be an TCP invites OnSeminar. So we have one speaker from the World Bank, which is talking about the works together with the task 35, and the topic is goes in direction of the flexible sector coupling. So I don't know in the moment who will all give the talks. Anyway, I'm happy if you want to join. And yes, with this said, I wish you all a very nice Easter holiday and a good afternoon.